We're going to find the volume of the solid of revolution obtained by rotating a circular region bounded by the circle x minus 2 squared plus y minus 3 squared equals to 9 about the vertical line x equals to 10. Now we'll be using the washer method. Note that this circle has center 2, 3 and radius square root of 9, which is 3. Now we're going to solve first for x in terms of y. So x minus 2 squared is equal to 9 minus y minus 3 squared. Taking square root of both sides, x minus 2 is equal to plus or minus square root of 9 minus y minus 3 squared. So x equals to 2 plus or minus the square root of 9 minus y minus 3 squared. Now we could simplify under the radical, but in fact it's better not to do it because it will be simpler to integrate. Now we can draw our circle and see what to set up our integral. Here is the axis, and first we'll find the center of the circle. It's at the point 2, 3. There's the center. We go 3 units down because that's the radius, down to the x-axis. 3 units up, that takes us up here when y is 6. 3 units to the left, that's when x is minus 1. 3 units to the right where x is 5. And now connect these 4 points in this kind of a circular fashion to draw this circle. Now also I'm going to draw this line. This is the axis of rotation, the line x equal to 10. Now what we solved for before was in terms of the right and the left semicircle. The left semicircle, which is what I'm pointing to here, has the equation x equal to 2 minus the square root 9 minus y minus 3 squared. And the right semicircle, which is what I'm pointing to here, has the equation x equal to 2 plus the square root of 9 minus y minus 3 squared. Now, pick any y between 0 and 6. Keep track of this horizontal slice inside the circle. 180 degrees into its rotation, that slice will end up here. And then full 360 degree rotation will give us a washer that looks like this. The area swept up will be the area between these two circles. So the key to solving this problem is to express the area between these two circles as a function of y. Recall that when we have a washer, any washer, we have a small circle, let's say its radius is little r, and a big circle, let's say its radius is big R. Then the area between the two circles is pi big R squared minus pi little r squared, or pi times the quantity big R squared minus the little r squared. For our case, the center of this washer is on the axis of rotation, the line x equal to 10. The big radius, right, goes all the way to here. That's our big R. And the small radius goes all the way to here. That is little r. We want to express these as functions of y. Let's start with the big radius. The distance from the axis of rotation to the y-axis is 10 units. But you can see that in this picture, big R is little more than that. Seems like we have to add, but notice that the x-coordinate of the left semicircle is negative because it's in the second quadrant. So we're actually going to subtract the x-coordinate of the left semicircle, which is 2, minus the square root of 9 minus y minus 3 quantity squared. So we have 10 minus a negative number, which will be positive. Therefore, big R will be a little bit more than 10. Simplifying this, this is 10 minus 2 is 8, minus a minus plus, square root 9 minus y minus 3 squared. Now little r is done similarly. It's 10 minus the x-coordinate of the right semicircle, which is 2 plus square root 9 minus y minus 3 squared. And simplifying this, this will be 8 minus the square root of 9 minus y minus 3 squared. We're now ready to set up the integral for the volume using the washer method. So the volume will be pi times the integral. We're taking our y's between 0 and 6. Big radius squared, so that would be 8 plus the square root of 9 minus y minus 3 squared minus the little r squared. That would be 8 minus the square root of 9 minus y minus 3 squared, and then this is integrated with respect to y. Let's do a little bit of algebra. This is pi times the integral from 0 to 6. 64 plus 16 times the square root of 9 minus y minus 3 squared, plus, when we square the square root, 9 minus y minus 3 squared. So that's the first part, minus 64 minus 16 times the square root 9 minus y minus 3 squared, plus 9 minus y minus 3 squared dy. Well, a lot of things fortunately cancel to make this integral a little bit easier. Notice 64 minus 64 cancels, and 9 minus y minus 3 squared minus the same thing over here cancel. The square root parts don't cancel because we have 16 minus a minus, so that's 16 plus 16. That gives us a total of 32. We also have the pi, integral from 0 to 6, times square root of 9 minus y minus 3 squared dy. Let's use this kind of substitution. U will take place of y minus 3. Notice that du is just dy. And then when y is equal to 0, u is going to be 0 minus 3, which is negative 3. And when y equals to 6, u is going to be 6 minus 3, which is 3. So the integral becomes 32 pi, integral minus 3 to 3, square root of 9, y minus 3 is u, so that's u squared, and dy is just du. Now, if we had to evaluate this integral from the beginning, we would have to, or from scratch, we would have to use a technique called trigonometric substitution. But we can do this integral without actually integrating, because if I let, say, w equal to the square root of 9 minus u squared, and square both sides, so w squared equals 9 minus u squared, therefore u squared plus w squared is 9. This is a circle in the UW plane with center, origin, and radius 3. And if we go backwards to the actual function we're integrating, this is the function we're integrating is the upper semicircle in the UW plane. So let's draw the picture. Here's what the upper semicircle, this is U and this is W. Here is the upper semicircle. Notice its radius is 3, so it's from minus 3 to 3. And this is the graph of w equal to the square root of 9 minus u squared. The integral is asking for this area. Well, we can find this area without integration. We know the area of a circle with radius 3 is 9 pi, so the area of a circle that's of half a circle will be 9 pi divided by 2. It's just a semicircle. So therefore, the integral is equal to 9 pi over 2, and our answer is we have 32 pi in front of the integral. The integral itself is 9 pi divided by 2. 32 over 2 is 16, so we have 16 times 9 times pi times pi. 16 times 9 is 144. We arrive at the final answer as 144 pi squared units cubed. For more videos,